Hello, this is Lipika and today I am going to present the presentation on climatology. The outlines will cover introduction to climate and the global climatic factors. So let's start. A climate is commonly defined as the weather averaged over a long period, generally over a period of 30 years, whereas weather reflects a short-term or momentary condition of the atmosphere. The basic zones of climate are hot and arid, warm and humid, and cold and dry. The scientists have categorized the climate into 5 major parts. Tropical: in this hot and humid zone, the average temperature are greater than 64 degrees Fahrenheit all around the year. Dry: these climate zones are so dry because of moisture is rapidly evaporated from the air and there is very little precipitation. Temperate: in this zone there are typically warm and humid summers and thunderstorm and wild winters. Continental: these regions have warm to cool summers and very cold winters. Polar: in these polar climates it's extremely cold. Even in the summer the temperature here never goes higher than 50 degrees Fahrenheit. Global climatic factors. The first point is climate and the tropical climates. Climate, in Greek it is called kalima and is defined in Oxford Dictionary as the region where conditions of temperature, dryness, wind, light, etc. It could also be defined as an integration of the time of weather conditions. Tropical climates are those where the heat is the dominant problem. Next is the solar radiation's quality. The earth receives most of its energy from the sun in the form of radiations. The spectrum of solar radiation extends from 290 to 2300 nanometers, in which 290 to 380 nanometers is the ultraviolet rays, 380 to 700 is the visible rays, and 700 to 2300 nanometer are the short infrareds. Due to the filtering effect of the atmosphere, the spectral energy distribution varies with the altitude. As a general value, 100 lumens per watt is used for solar radiations. Next is the solar radiation's quantity. The intensity of variations reaching the upper surface of the atmosphere is taken as the solar constant, which is 1395 watt per meter square, but it may actually vary plus minus 2 degree due to variations in the output of the sun itself, and it varies plus minus 3.5% due to its change in the Earth-Sun distance. Earth moves around the sun in slightly elliptical orbit, and one revolution is completed in 365 days, 5 hours, 48 minutes, 46 seconds. This orbit results from the gravitational pull of the sun and the centrifugal force due to the Earth's inertia and momentum. At aphelion, the solar distance is 152 million kilometers, and at the perihelion it is 147 million kilometers. Next is the tilt of Earth's axis. The Earth rotates around its own axis, making an 1 day of 24 hours. The axis of rotation is tilted to the plane of the elliptical orbit at an angle of 66.5 degree, and the direction of the axis is constant. The maximum intensity received on a plane normal to the direction of radiation. Due to the tilted position, the area receiving the maximum intensity moves north and south between the Tropic of Cancer and the Tropic of Capricorn. This is the main cause of seasonal changes. On 21st June, the Tropic of Cancer receives maximum sun and hence experiencing the longest daylight, whereas the Tropic of Capricorn receives the minimum sun rays and hence experiencing the shortest day. On 21st March and 23rd September, areas along the equator are normal to the sun rays and hence have the equinox days. Next is the solar radiations at the Earth's surface. It can be determined by 3 points. The first is the cosine point, cosine law. It states that the intensity on the tilted surface equals the normal intensity times the cosine of the angle of incidence. That is, the same amount of solar radiation can be distributed over a larger area. The atmospheric depletion, it is the absorption of radiation by ozone, vapors and dust particles in the atmosphere. The duration of sunshine is the length of the day period. Next is the Earth's thermal balance. The total amount of heat absorbed by the Earth each year is balanced by corresponding heat loss. Without this cooling, the thermal balance of the Earth could not be maintained. The temperature of the Earth and its atmosphere could increase and would soon cease to be favorable to most forms of life. The Earth's surface releases heat by three main processes: the long wave radiations, the evaporation, and the convection. Wind thermal forces. Winds are basically the convection currents in the atmosphere trending to even out the differential heating of various zones. The pattern movement is modified by the Earth's rotation. At the maximum heating zone, the air is heated up by the hot surface. It expands, its pressure is decreased, it becomes light, and so it rises vertically and flows at a higher level towards the colder regions. The part of this air having cooled down at the higher level descends to the surface of the subtropic regions, from where the cooler, heavier air is drawn in towards the equator from both north and south. The area where the air rises, where these northerly and southerly wind meets, where the tropical front is formed, is referred to as the intertropical convergence zone. This area experiences either extremely calm condition or very light breezes of irregular directions and is referred to as doldrums. Trade winds or the Coriolis force. The atmosphere rotates with the earth as it is light in weight and behaves as fluid against the earth's surface only by gravity and friction. It has tendency to lag behind the earth's rate of rotation, where this rotation is the fastest, that is at the equator. There is a slippage at the boundary layer between the earth and its atmosphere, caused by what is known as the Coriolis force. This effect is experienced as a wind blowing in the direction opposite to that of the earth's rotation. Actual wind is the resultant of thermal and Coriolis force. The northeasterly winds of north of equator and southeasterly winds south of the equator, these are known as the northeast and southeast trade winds. Mid-latitude westerlies. Around 30° north and south, there are two bands of continually high barometric pressure. Winds in these zones, typically light and variable, between 30° and 60° north and south. However, strong westerly winds prevail, blowing in the same directions as the Earth's rotation. It can be explained by the law of conservation of angular momentum. The total angular momentum of the Earth's atmospheric system remains constant. That is, if it is reduced at the equator by easterly winds, this must be compensated by for westerly winds elsewhere. Polar winds. Towards the pole from latitude 60° north and south, the air blows pattern comes under the influence of thermal factor. The pattern is similar to that of the equator. Air at the sun surface moves from the coldest to the slightest warmer regions. As the circumferential velocity of air at the poles is almost nil, the air will lag behind the rotating earth as it moves away from the poles. The northerly is deflected into northeasterly and the southerly into the southeasterly polar winds. At the meeting point of cold polar winds and the mid-latitude westerlies, a band of low pressure, a subpolar front is formed with highly variable and strong winds. Annual wind shifts. During the course of each year, the global winds pattern shift from north to south and back again, remaining broadly symmetrical about the ITCZ. The location at the ITCZ follows the maximum solar heating. The extremely north and south position of the ITCZ are in north July and in the south January. As the consequence of this annual shift, most regions of the earth experiences seasonal change not only in the temperature but also in the wind direction and in the rainfall. The influence of topography. On the continental scale, wind and weather are the result of an interaction between the broad global flow pattern and the region pressure and temperature patterns created by the sun's differential heating effect on land and forest and water. The force, direction and moisture content of air flows are strongly influenced by topography. Air can be diverted or funneled by mountain ranges. Air flows detected upward as it cools release its moisture content. A distant air mass will very rarely give any precipitation. Therefore, rainfall characteristics vary sharply between the locations on windward and leeward slopes of the mountain ranges. The humidity of air will vary with the rate of evaporation of the moisture from the surface below. That is, it depends upon the availability of the water to be evaporated. The air movement can be generated on quite a small scale. It can be generated between a lake and its shores, between a town and its surrounding countryside, between a sunny and the shaded area of the large building. Thank you.